Chapter 5, Section 6, Differential Equations, Growth and Decay. Now, we have talked a little bit and worked with differential equations in previous sections, and we've separated the variables and integrated both sides to solve for our variable y. So we're going to approach it the same way, but we're going to introduce some examples of applications that can be done, including exponential growth and decay, and if we have time, even do an example of Newton's law of cooling. So first things first, when you have a differential equation, and differential equations typically are equations in terms of x and y and derivatives of y with respect to x, so it might look like this or it might look like that. Here's an example. You want to separate the variables. So what I usually do is, if it's y prime written down, I write it as dy dx, so that I have my y and my x here. And then I separate the variables. It is as if, and although I'm not really doing it this way, but it is as if I am cross multiplying. I am rewriting this first step in terms of differentials. Dy equals 3x squared over y squared dx. And then I'm dividing, or in this case multiplying both sides by y squared. So I end up with something that looks like this. I'm going to integrate. I integrate the left side, I integrate the right side. I only put down 1 plus c because that's all I really need. I multiply through by 3. Now you really don't have to, but since I'm multiplying c by 3, just to show that it, unless c is 0, that it's different, I write c sub 1, and then I take the cube root of both sides, and I get this. I have solved my differential equation when I have y all by itself. Most of the differential equations that we'll look at, they want you to solve for y, but there are differential equations very difficult to solve for y. And that's something that you'll probably study somewhere along the lines in college. So a differential equation is said to be separable if f can be expressed as a product of a function of x and a function of y. With what we covered, as I mentioned before in the first half of the chapter, we're going to consider applications of differential equations involving exponential and logarithmic functions. So that's where we're going to get our growth and decay. Now, what types of topics study growth and decay? Well, you will see exponential growth and decay in most math textbooks, from algebra up through calculus, business classes like linear algebra, not linear algebra, what am I thinking of? Not college, business, let's see. Oh, for the life of me, I can't remember. It'll come to me before this video is over with. But we're talking about growth or decay in populations, money, radioactive element samples. It's an increase or decrease at a rate that is proportional to the amount present. That's the key. The rate is proportional to the amount present. So if I write the rate with respect to t here is equal or proportional to the amount, which is y present, I have my k, which is my constant of variation or constant proportionality. So this is the differential equation that I start with, and you should be able to go, as it turns out in this problem, from start to finish on this by rewriting this, separating the variables, integrating both sides. All right, I get the natural log of the absolute value of y is equal to k times t, because I'm integrating with respect to t here, plus my constant. I'm solving for y, so I raise both sides to base e. And of course, e to the natural log of the absolute value of y, these are inverse functions, so I just get the absolute value of y is equal to, now over here, I had all of this as my exponent, but because I can use my properties of the product of powers of exponents, I can rewrite this into this form. Because remember, if they have the same base and you're multiplying, you add the exponent, so I'm just reversing that. Now, this guy here, e to the c, that's a constant, which I can call c sub 1 if I want to. I drop the absolute value, kind of pick up the plus or minus. Normally, they're going to give you an initial condition here so that you can determine if it's plus or minus, but I'll just write all of this as c sub 2, and then you'll hopefully see here that the law of exponential change, if y changes at a rate proportional to the amount present, that's this guy, where y is c when t is 0, then it looks a little bit like y equals kect. Okay, if k is greater than 0, you've got a problem that involves growth, exponential growth. And if k is less than 0, you've got exponential decay. And of course, k is called the rate constant, although when we wrote it down here, it was called the constant of proportionality. So let's try an example here, something very basic, something you would see in an algebra book. it says the rate of change of y is proportional to y. Now, what that means is dy dt is equal to k times y. Now, I just showed you here that when that's true, we get this. You don't have to solve it every time, but you should be able to solve it as I showed in the previous steps here. You should be able to do these steps. If I could set my paper still, you should be able to do these steps. If you're not sure if you can, then you should practice this until you feel comfortable with it, and then after that you can just assume that if it says that the rate of change of y is proportional to y, that you can go right to this y equals kect looking thing here. So that's what this is going to give me. Y is equal to ce to the kt. Now it says here that when t is 0, y is 3. So I plug in. When t is 0, y is 3. Well, of course, this is just going to be 0. E to the 0 is 1. C is equal to 3. That's my initial amount. That's what it was talking about back here. Y is c. That's this guy right here when t is 0. So c in this case turns out to be 3. That gives me y equals 3 e to the kt. Then it says y is 2. Excuse me. When t is 2, y is 6. When t is 2. And t is 2, so that's going to be 2 times k. I'm going to divide both sides by 3. I'm solving for k. I'm going to take the natural log of both sides. I have to come up here now. So I'm going to get the natural log of 2 is equal to, now this guy right here, I have the natural log of e raised to a power, it's just that power. So I get k is equal to 1/2 the natural log of 2. Then it says, what is the value of y when t is 4? So now I have to take this, and I'm not going to change it to a decimal quite yet. I'm going to get there, trust me. But that goes in right here. So now, and I don't think I've given myself much room here, y equals 3e to the, that's going to be the 1/2 natural log of 2 times t power. So it says, what's y when t is 4? Plug a 4 in here. I have y equals 3e to the 1/2 natural log of 2 times 4. Of course, 4 times 1/2 is 2. So that's going to be 2 natural log. You get it? Natural log of 2. And if you use your power of logarithm, I can bring this up as an exponent. That's going to equal 3e to the natural log of 2 squared, which of course is 4. But see, here's that inverse property again. E to the natural log of a power is just that power. Oops, 2 here, not a 4. It becomes a 4. This is 4 here. So all of this, way back over here now. Sorry about that. I'm all over the place. Y equals 3. And then this is going to be e to the natural log of 4 is just going to be 4. So I get 12. And that's my answer. That was a mess. And I didn't have to go with a decimal approximation here because I was lucky enough to get my values to simplify nicely. All right, now let's look at exponential decay. By the way, I want you to note here that in this particular problem what k is, because I went first starting with 3 and then ending up with 6, and I want you to look at this right here. 1/2 natural log of 2 is equal to k. Now let's see what happens here in this problem, because in this problem we're talking about half-lives. This was doubling, this is half-lives. Now it says how long will it decay until you have 20 grams of this carbon-14. Suppose we have 100 grams of carbon-14. How long before we can get this thing to decay all the way down to 20 grams? Okay, so what I'm going to have to do here is this is the example of using the law of exponential change. It doesn't say it here in the problem because I was too silly or too lazy to write it out, but this is going to involve that. This is half-lives, and that definitely follows the law of exponential change. So that's going to give me y equals ce to the kt. Now c should be my initial amount, and we have 100 grams to begin with, so c is 100. Now if you don't trust me, plug 0 in for t and 100 in for y, and you'll see that c turns out to be 100. So now I have y equals 100 e to the kt. And it says how long before I have 20 grams. Well, I need to know what k is. So the half-life, by the way, and this is in the textbook. I cannot remember what page. I think it's like page 363 that's got a table of half-lives for various types of radioactive material. And I think it's 363, 64, somewhere in there. And I think it's 5720. Is it 5720 or 5730? Oh, I hate it when I do dumb stuff. I may have to look this up on my computer here that I just happen to have close by, because I did not bring a textbook, and that was stupid on my part to have a textbook with me. But I think I can probably get this Googled and not waste too much more time on, of your time here on this video here. So let me just real quick double check. Half-life of carbon, there it is, carbon 14, 5730. Oh, it wasn't right. 57, good thing I checked. So according to scientists, it's supposed to be 5,730 years. So that means if 5,730 years goes by and we started with 100, we'd end up with 50. Now this is going to go all the way down to 20, which is half, and then half again, and even smaller than that. So I'm thinking this is going to be probably 12,000, 13,000 years by the time we get done here. But I need this to figure out K, because if I have 5,730 years, that means I'm going to have 50 grams of this stuff. 5,730, there we go. And I'm going to divide both sides by 100. So I get 1/2 equals e to the 5,730k. I'm going to take the natural log of both sides. And I better move this up so you can see what I'm writing here. And of course, natural log of e raised to a power is just that power. So that gives me the natural log of 1/2 is equal to 5,730 k. So k in this case is equal to 1 over 5,730, the natural log of 1/2. Oh, this is interesting. All right, so now what is that going to give me? Well, that's going to give me the value that I'm going to plug right in here. I have y now equals 100. Hopefully you'll be able to read this because my handwriting's not very good. 5730, the natural log of 1/2 t. And I'm going to plug in 20 right here in for y. So I get 20 equals 100 e to the 1 over 5,730 natural log of 1/2 t. And if I divide by 100, I get 0.2, or 1/5, is equal to e to the 1 over 5,730 natural log of 1/2 t. I'm going to take the natural log of both sides. Yikes. This just gets messier and messier. If I was smart, I would have written this out as a decimal. Natural log of 1/2 t. And of course, that means I'm going to have the natural log of e to a power is that power, so I have 1 over 5,730 natural log of 1/2 t is equal to the natural log of 0.2. I'm going to divide both sides by this number. So I'm going to get t is equal to, and I got to get Mr. Calculator out of the drawer here real quick. Maybe I've done this on separate paper. I should have done this ahead of time. Let's see, and what a mess this is going to be. I'm going to have the natural log of 0.2 divided by, and then in parentheses I'm going to have, where is it at? Oof, 1 divided by 5,730 times, what is it here? Natural log of 1/2 times the natural log of 0.5, and let's see, well, I don't know if you can see that very well. Oops, you can't see that very well here with this up on the screen. There we go. So I get 13,000, can't read my own print there, 304.648. So it didn't say how many decimal places. I'll go ahead and round it to 3. Now, the only thing I really didn't do very well, besides not leaving enough space here, is leaving enough space to write out my answer. Because this is kind of a story problem setup, I would expect you to write out the answer. So how long will it take before it decays to 20 grams? It will take 13,304.648 years to decay to 20 grams. Not a great statement of answer, but that's about as good as I can do with that space right there. Okay, let me jump over this guy here. I'm hoping you can see this okay. It says, consider the world's population in 1975, which was about 4 billion people. The world's population growth was 2%. Now, by saying that, I'm saying that it's, let's say on the average about 2%, because of course it changes from year to year to year, although it should stay pretty close to this. And so in this case, k is equal to 0.02. They will sometimes give you this extra information. The following function models this with y equals 4 billion e to the 0.02 t. Find the population in the year 2000, and how long will it take until the population doubles to 8 billion? Well, in the year 2000, that means here that you're starting with 1975, that t is 25. So I'm going to have to plug for the first part 25 in. All right, and as it turns out, I had the forethought to at least grind this out on a calculator before I came in and started this video. I get this to be 6,594,800,000 people. Now, definitely rounded here. Okay. So then it says how long until the population doubles to 8 billion. So now I'm going to plug the 8 billion in for y. So let's see, it's 3, oh, got to count to 3 here first before I start putting them in. Okay, so 8 billion equals 4 billion. Whew, should leave more space. E to the 0.02 t. I'm going to divide both sides by 4 billion. Now notice here, this is a little like one of the first examples I did where I end up doubling. So that would give me, if I divide both sides by 4 billion, I get 2 equals e to the 0.02 t. I take the natural log of both sides. And I get, of course, this is just 0.02 t is equal to the natural log of 2, and that means that t is equal to the natural log of 2 divided by 0.02. So, did I punch this out on the calculator? Yeah, I did. And this turns out to be, to the nearest year, it turns out to be 35. So it's going to take 35 years before the population doubles from 4 billion to 8 billion, and this was 1975, so that'd be 2010. I'd have to check on the on the computer, see what the world's population was in 2010. But now I would answer both of these problems in words. I just did not leave myself very much space here. But I would answer this. It says the population in 2000 was, and then write it out. Don't just do that. And the population doubles in 35 years. And that would be the answers for the 2 parts there. Now, the reason I keep talking about doubling and such is that there's a little shortcut that you can use that I have written down right here that talks about how much time it's going to take for doubling time and how much time it's going to take for a half-life or a half-time. Okay? Now, there is also the rule of 72, which you can use for really rough estimates for doubling time, because you just take the number 72 and you divide it by whatever the rate is of growth. Now, if the rate is like 8%, R would be an 8 here, and 72 divided by 8 would be 9. It would take approximately 9 years to double. So that's always handy. It's just an approximation, though. This would be a good thing to keep track of as you're working some of these problems out. All right, almost done with these notes, and this is also telling me right now, since I still have two examples to do, another one of my long videos here, which I'm sure you guys are getting tired of, but let's see if we can get through these two examples. I'd like to get to this Newton's law of cooling. During an experiment involving crow flies, as it is discovered, their population grows exponentially. There were 1,000 of these flies after the second day of the experiment, and 3,000 of these flies after the fourth day. And we're to approximate how many flies were in the original population. So they didn't give us this. We're going to assume that since it grows exponentially and there were 1,000 on the second day, that it's probably less than 1,000. And well, let's see what happens here. Well, first things first, this is one of those problems that involves the law of exponential change. So I'm going to write y equals ce to the kt. I just don't happen to know what c is. T is in days, it looks like here. So we know that y is 1,000 when t is 2. So I have 1,000 equals ce to the k times 2. And I also happen to know that I have 3,000 on the fourth day. So that would be 3,000 equals ce to the k times 4, the fourth day. Now I can take this guy here. This is 1,000 equals ce to the 2k, and I'm going to divide both sides by e to the 2k so that I can conveniently solve for c, because this c is the same as this, and now that tells me I can plug this in right there. So I have 3,000 equals 1,000 over e to the 2k, that's in for c, times e to the 4k. Well, this is 3,000 equals, now these are both e raised to powers, and it's a product, so I can cross cancel here, and I subtract the exponents, and I would get 4k minus 2k is 2k, so I get 1,000 e to the 2k. Divide by 1,000, I get e to the 2k is equal to 3. I take the natural log of both sides. There we go, and I can use my property of inverse functions here, and I get 2k is equal to the natural log of 3. K is equal to the natural log of 3 divided by 2, or 1/2 the natural log of 3. So let's see, did I punch this out on a calculator? I sure hope I did. I did, and I have this to be approximately 0.5493. Now, it'd be great if that's what I wanted, but it said how many flies were in the original population, so what I really want is c. So I'm going to take this guy right here, and I'm going to plug this in for k, and I'm going to get c is equal to 1,000 all over e to the 2 times 0.5493. Yikes, so I multiply through by 2, raise the e to that power, and then divide it into 1,000. And if I've done this right, and I hope I wrote this one down as well, to the nearest fly, I get 330. Well, that kind of makes sense, because I had 1,000 after 2 days, so I knew it was going to be less, but I didn't think it was going to be like 10 or 20. I figured it was going to be probably around 400, and that doesn't seem to be so bad. So how many flies were in the original population? There were 330 flies, crow flies, in the original population. Okay, my last example here, I don't think I've got enough space here in this because I have to kind of derive this one. This involves Newton's law of cooling. You know, you get a hot cup of coffee, you set it down on the counter and walk away. By the time you get back, you know that your coffee is going to be closer and closer to the actual temperature in the room in which you've set your cup of coffee down. So we're going to use what we know about solving differential equations to come up with Newton's law of cooling here, which states that the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. Excuse me, I must be allergic to physics here. This looks like a physics problem. Let Y represent the temperature in degrees Fahrenheit of an object in a room whose temperature is kept at a constant 60 degrees. Now that's chilly. We assume Fahrenheit. If the object cools from 100 degrees Fahrenheit to 90 degrees Fahrenheit in 10 minutes, how much longer will it take for the temperature to decrease to 80 degrees? Well, let's see what we can do here. Let's see. We know that it's proportional. The rate is proportional to the difference between the object's temperature of surrounding medium. So that means that dy dt is proportional to the difference in the object and the surrounding temperature, which was 60 degrees here. So if I separate the variables, I get dy over y minus 60 equals k dt. I integrate both sides. I get the natural log of the absolute value of y minus 60 is equal to kt plus a constant. Oops, plus a constant. Now it says here the object cools from 100 to 90 in 10 minutes here. So that means when t is 10, the object has cooled down to 90 degrees here. So what does that give me here? Well, that's going to, well, I tell you what, let's get rid of the natural log first. So that's going to give me the absolute value of y minus 60 is equal to e to the kt plus c. And I'm going to get, now, this is absolute value because of the natural log, but since my temperature is already warmer than the 60 degrees, y is going to be greater than 60. I can drop the absolute value. Y equals 60 plus e to the kt, and then of course plus c, that would be times e to the c. Let me see if I can write this a little bit better. I get y equals 60. I'm going to call this c sub 1 e to the kt. All right, now that's the guy I'm used to dealing with here. So in this case, when t is 10, it goes from 100 to 90. So I have 90 is equal to 60 plus, well, hang on a second here. Let's see if I can get this figured out for sure. I want to make sure that, oh, you know what? I jumped the gun. I haven't done this problem in about a year. Let's see. Jump the gun here because I know that when t is 0, I'm at 100. So I'm at 100. When t is 0, and so that's, of course, that's just going to be 1, so I get c sub 1 is 40. So now I have y equals 60 plus 40, that's the c sub 1, e to the kt. Now, if I go 10, I'm at 90. So I plug 10 in for t there, that would be 10k. Oh, I smoke. Subtract 60, I get 30 equals 40 e to the 10k. Divide by 40, I get e to the 10k. Sounds like a race. Is 0.75. Take the natural log of both sides. I didn't think I was going to have enough space here, but maybe I can. So I get 10k is equal to the natural log of 0.75. Maybe not. So k is equal to 1/10 the natural log of 0.75, and that goes right, if I can find my spot here, right here. Maybe I left enough room in the middle. I don't think I did. Let me erase this so I have some more space. If you're taking notes, just go ahead and get another sheet of paper here so you don't have it all so messy like I am. So now I have y equals 60 plus 40 e to the kt, but k is 1/10 the natural log of 0.75 times t. Now it says, how much longer will it take before it decreases to 80 degrees? So I'm going to plug 80 in here for y. I'm going to subtract 60, and that's going to give me 20 here, and then I'm going to divide by 40, so I get 1/2 e to the 1/10 the natural log of 0.75. Do I have that here? 1/10 t here. Now, this is just getting messier and messier here. So what I'm going to have to do here is I'm going to have to solve for t. I could take the natural log of both sides, divide both sides by 1/10 the natural log of 0.75, and I get, no space, back over to here, I get t is equal to, let me grab my calculator, bend this sheet of paper so you can see it. There you go. Sorry about that. Wow, that's really weird the way it lights up like that with my hand and then it gets so much darker. I guess I should have noticed that videos ago. So let's see. 0.75. Let's see. Natural log of 0.75 divided by 10. Oops, hang on a second. I messed up. There you go. Clear. Looking at the wrong thing. Natural log of 0.5 divided by 0.1 times the natural log of 0.75 equals, and I get 20. I get, oh, you can't see that. I get 24.094, 24.094. So it's pretty close to 24 minutes. So it says, how much longer will it take? Well, you'd already waited 10 minutes for it to drop to 90. So altogether it's 24 minutes. So it will take another 14.094 minutes to cool to 80 degrees. All right. That one was a peach. Now, why would I show you a problem that messy, especially if it's something that you're going to study in physics? It's because I have seen Newton's law of cooling on the practice AP problems in the past, old exams. So it doesn't hurt to try a problem out with that. Now, we did some of this last year in pre-calculus, but we didn't derive the formula. We just went ahead and gave you the formula to use. So you could always, of course, Google that and be able to use it. But as you can see, it is derived from a problem very similar to what we were talking about before with the law of exponential change. Make sure that you practice these problems.